These are the notes on the periodic table. We already mentioned that chemistry is the study of matter. We talked about how many flavors there are. Those flavors are, of course, the elements. The way we organize the elements is on the periodic table. The periodic table of the elements tells us many, many, many things about the different flavors of matter. So we are going to talk about some of the information that you can find on the periodic table and why it is organized this way. I prefer to cover this part first and then go into the underlying atomic structure because I think it helps in your understanding. If you're talking about a periodic table, it's not necessarily a table like a kitchen table. It's more a table like a chart, although you can make a table out of it. There was one guy who made a periodic table that you could literally sit at, and each of the boxes had a sample of as close as you could find to the pure element. And you would not want to sit in certain portions of that table. You would not want to sit, for example, down over by that radon, or let's say down at the other corner over by uranium, which is off the picture. Certain areas you would want to avoid. When you're talking about the numbers on the periodic table, a lot of them are counting things up. They're either counting up protons or protons and neutrons. Sometimes you can figure out the number of electrons from the numbers on the periodic table. Now, you have learned about these subatomic particles before. These are the ones that make up the atom, but you might not have ever been told which of the three is the most important. Well, I'm going to tell you now. There is one of these three subatomic particles that is clearly the most important for determining the element, and that is the proton. The proton always determines the element. If you know the number of protons, then you know which element it is. That is what we call the atomic number. It's the count of the protons. Since protons have a positive charge, the atomic number is also the count of the positive charge from the nucleus. So if you have one proton, you have a +1 charge, and if you have 5 protons, you have a +5 charge from your nucleus. Neutrons are not counted anywhere directly on the periodic table, but they are included in the mass number. Protons and neutrons are both included in the mass number. And then electrons are never explicitly listed on the periodic table. However, you can figure out the number of electrons based on their attraction to protons and based on whether or not you have what we call ions. We'll talk about that in atomic structure. Remember that based on Coulomb's law, that equation there in yellow, electrostatic forces depend on charges. If you have two charges that are opposite, opposite charges attract. The amount they attract depends on how much charge and how far apart they are. And then like charges repel. So notice if you have two negative charges, like two electrons, they push each other apart. And then, of course, it's divided by the distance squared. That's what the r squared is, the distance between them. And that means that the attraction or repulsion is only really strong when they're close together. If they're far apart, the force decreases rapidly. That's called the inverse square law. We'll discuss this more when we get into the atomic structure, but because of this, basically, if you're talking about atoms, whenever you have a plus, like a proton, you're going to have a minus, like an electron. So using that logic, you can usually determine the electrons in an atom just by looking at the periodic table. It's important to realize that the mass of an electron, proton, and a neutron, the masses of those are very different. The electron has an itty-bitty little mass. We can call that 1 electron mass. A proton, on the other hand, is much, much more massive. Not compared to us on our big macroscopic scale, but in the nucleus of the atom, the proton has a mass that is 1,837 times greater than the mass of an electron. The neutron, on the other hand, also has a mass that is 1,800 and 42 times the mass of an electron. So notice that the mass of a proton and the mass of a neutron are very, very close together. They're very similar. They're about 99% the same. And their masses are much, much greater than the mass of an electron. This means that the mass of an atom comes almost entirely from the mass of its protons and its neutrons. That's why we count up the protons and neutrons to get the atomic mass. Now, when you look at a box for an element on the periodic table, like this one here, you sometimes get different information on different periodic tables, depending on what they want to show you. What you usually get, you often get, is the name of the element. Now, the only problem with that is the name is in one particular language, in this case, English. And not only that, but in English, some elements can have more than one name, depending on the country you're in. So that gets a little tricky. We want to have a periodic table that applies anywhere in the world, in any country in the world. So what we have agreed on are the symbols. The symbol of an element is agreed upon by every country in the world, and everybody uses those. So in the case of oxygen, the symbol is O. Another thing that is included is the atomic number, in this case 8. That is the atomic number for oxygen. That is the number of protons that you always have if you have oxygen. They could have called oxygen element number 8, and they wouldn't have had to give it its own name, but they decided to go with names that people had come up over the years when they organized the periodic table. So oxygen is element 8. Oxygen has 8 protons. Then we have the atomic mass. Well, the atomic mass is all the protons and the neutrons in the atom added up. It doesn't show the neutrons on their own, but they are included in this number. Well, since we already had 8 protons, well then there must be 8 neutrons to add up to 16. The other thing about the atomic mass is it includes all the different isotopes. Because there are different kinds of oxygen, actually, there's different isotopes of oxygen. Some of them might have 7 neutrons, some of them might have 8 neutrons. So depending on the number of neutrons they have, well, that changes their mass. And then if you average in all of those masses, you get the atomic mass. Or sometimes this is called the atomic weight because it's a weighted average. Now, in the case of oxygen, the isotope oxygen-16 is so overwhelmingly abundant, and the other ones are so relatively rare, that it rounds off to 16.00. If you were to go one more digit, then you would have 15.999, but it does round off to 16. So just keep in mind, you can tell certain things by looking at the periodic table. The other things that can be included on periodic tables could be electronegativity, or density, or freezing point, or boiling points, which this one has some of those on it. But typically those are not included on a normal periodic table. The man who is credited with creating the periodic table is the Russian scientist Mendeleev. Now, Mendeleev did a lot of it. He actually helped put them in a format that was very much like the periodic table we use, but maybe turned sideways, kind of, and there were many elements that were as yet unknown. But he was only one of many, many people along the way. Many, many people who contributed to the development of the periodic table. So we have a tendency to give all the credit to one person, but obviously science is a team effort. It takes the work of many, many people over many, many years to make a lot of developments in science. So if you had to know one person, yes, Mendeleev is the one, but there are many, many others involved. The periodic table has one gigantic division. The one thing that divides the periodic table into, let's say, 2 big parts. And it's a very, very simple division, something that you probably already know about, something that isn't going to trick you or confuse you. It's the difference between the metals and the nonmetals. And the metals on this periodic table that I made are all the elements that have a pale blue background. The ones that have that pale green background are another group, and the ones that have that pale purple background are the third. But look at all those metals. Metals are probably what you think they are. They're materials that look like these images here. You'd probably know a metal if you saw it. You'd probably know if something was not a metal if you saw it. Most of the time, you would be correct. This is one of those situations where your prior knowledge and intuition really help you in chemistry. That does not happen all the time. Some of the things you may have learned may work against you in chemistry, but in this case, what you know is probably right. Here is a list of the properties of metals. If something is a metal, it should be shiny, or we even call it metallic in appearance. It should be a solid at room temperature. It should have a high melting point. It's hard to melt it. High density, you know what that means. Large atomic radii, that means big atoms. Low ionization energy, we'll talk about that later. Low electronegativity, we'll also discuss that later. Usually high deformation, that means the ability to bend it. You can bend it back and forth. Malleable means the ability to flatten it into a sheet to hammer something flat, as you can see in the picture behind. Ductility, ductile, means you're capable of pulling it into a wire, which you can see coiled up right there, some copper wire. Thermal conductors, they conduct heat. Electrical conductors, they conduct electricity. That is what metals are supposed to do. But not every metal does all of these things. This is a list of properties that metals are expected to have. However, metals do not need to have all of these properties. They just need to have most of them. We find several metals that are lacking in one or more of these properties, but we find none that we call metals that are lacking half of them. So for example, solid at room temperature, well, there is a metal that is not solid at room temperature. You can probably think about it. We used to use it often in thermometers and in thermostats. Okay, we'll discuss that in a moment. And if it's not a solid at room temperature, well, then it also would not have a high melting point. Okay. And there's a few other things that do not always apply to every metal. Not every metal is equally good at conducting heat or conducting electricity, but they tend to do that. Okay. So think about this list. This explains why we make certain things out of metals. It obviously explains why we make wire out of metals. It obviously explains how we make pots and pans out of metals, because first of all, they are malleable. You can hammer them into a sheet, fold that into the shape of a pot or pan, and they are great thermal conductors for cooking with. Okay. The high density is related to the high melting point. There's sort of a relationship there. A bunch of these concepts are interrelated, but what they all depend on, the number one thing that makes metals metals, is that large atomic radii. Metals turn out to be the largest atoms. And we're going to understand why that makes them metals later on. But for now, just remember that a lot of these properties go hand in hand. They are related to each other. Platinum is probably the perfect little metal you could think of. Every single thing we just saw on that list of properties applies to platinum. So some metals are just perfect metals. They do every single thing on the list. So if you had to picture a metal in your head that obeys the properties of metals, platinum would be a good one. If you had to think of a weird metal, one that doesn't obey all the properties of metals, well, mercury is your best candidate, because mercury is not a solid and it does not have a high melting point. Okay, mercury is actually a liquid at room temperature on the surface of the Earth under 1 atmosphere of pressure. It's a liquid. So that makes it behave very differently. It flows around like water, but it has a higher density than water. It beads up differently, has a different surface tension. This is a fountain located in Spain, in Barcelona, Spain, in the Miró Museum, where they have replaced water, there's no water in this picture, with mercury. You can see the mercury flowing through the fountain just kind of like water would, but in some different ways. The way it drips down, if you notice, is a little different. The way it holds together, the way it beads is different. And that reflectivity on the surface there, part of that is just a reflection of the outside light, and part of that is the metallic surface. It actually does have a metallic, shiny appearance. If we zoom in, you might be able to tell more about the differences. So even though mercury doesn't obey all the properties of metals, it does obey most of them, and so we classify it as a metal. It falls into the metal category. There are some things that don't meet any of the properties of metals, and so we came up with the wonderful name nonmetals for those. A great example of that would be neon. Neon doesn't obey any of the things on the list. Okay? Neon at room temperature is not a solid. It's not even a liquid. It's actually a gas. It has a low density because it's a gas. It is a terrible thermal conductor. It is a terrible electrical conductor unless you turn it into plasma. That's a whole nother story, like they do in neon bulbs, like you see that dragon right there, has neon inside it. And by the way, there is no such thing as neon green or neon whatever. That is the color of neon. It's kind of a pinkish red color, and it's always that color. So anything else that you call neon is incorrect. I think what they're trying to say is that it seems to be glowing like neon, but neon is a particular color, so that is a bad usage of the term. There are other nonmetals that may have a couple of things in common with metals, like they might be solids, for example. Carbon is a good example. Carbon is a nonmetal, even though it is a solid at room temperature. In its different forms, it can be a diamond or it could be graphite, and there's others we'll talk about later when we get to it. But all of the forms of carbon are solid at room temperature. But if you tried to make carbon into a wire, good luck. If you tried to make carbon into a sheet, hammer it into a sheet, well, with the graphite, it would just break into little tiny chunks. With the diamond, it would probably damage your hammer. Tried to make it into a sheet of diamond. So carbon doesn't do the other things on the list, and it doesn't have large atomic radii, it doesn't have low ionization energy, and so on. So if something doesn't meet the majority of things on the list for metals, that makes it a nonmetal, even if a couple of them do apply. So when we look at the periodic table, it's interesting to note that the vast majority of elements are considered metals. Out of the 118 elements on the whole table, 92 of them are metals. Only 20 of them are nonmetals. So only 20 out of 118 are nonmetals. And what about the rest? Well, there are just a few, very, very few elements that they couldn't quite put in either category. They're not exactly metals because they don't have most of the properties, but they're not exactly nonmetals because they're close to 50-50. They have about half the properties. So these fall right on the line in between the two groups. These are called the metalloids. Metalloids act a little bit strange, and they have certain interesting uses, like silicon, for example, we use in computer chips because it is what we call a semiconductor. So if you look at these percentages, if you put them into percentage form, that makes 17% of the periodic table nonmetals, 5% metalloids. Add those together, what do you get? Okay, what do you get? 22%. So what's left for the metals? What percentage of the periodic table must be metals? The periodic table is 78% metals. If we go by the number of elements there are and how many of them are metals, 78% of the different elements on the periodic table are metals. So that probably makes you think that we live in a metal universe. When we look around us, we should see metal everywhere because there are so many metals, right? Well, no. Because what that depends on is something we call abundance. Abundance is very, very different than just the number of different elements that exist. It's how commonly we find them. Abundance is how commonly something is found in the world around us. So if something is abundant, there's lots of it all over. If something is not abundant, Okay, if it's scarce, then it's not found very often, and usually we hold those things a little more precious. Okay, if something is incredibly abundant, so abundant that we can't avoid it, everywhere we look we find it, then it is what we call ubiquitous. Ubiquitous means found all over the place, everywhere you look. So for example, water is ubiquitous on the surface of the earth. If you look around the surface of the earth, it's hard to avoid finding water. Like think about all the oceans on the planet. Okay? So when we consider abundance, this changes everything about what we find in the universe. So when you consider it based on abundance of the element, how easy it is to find the element all around you, how much of it is there, well, clearly things look a lot different. In this case, hydrogen becomes number one. Can you imagine what number two probably is? If hydrogen is number one, what's probably number two? Well, it is helium. These are abundance in the universe. These are the most abundant elements in the universe. Hydrogen, helium, and then oxygen and neon, nitrogen, carbon. Do any of those sound like metals to you? That's because they're not. Then there's silicon and magnesium. So magnesium actually is a metal, and then iron is a metal. But if you look at this list of abundance in the universe, now by the way, these are compared to silicon. So compared to the abundance of silicon, carbon is 3.5 times more abundant, right? And hydrogen is 40,000 times more abundant because hydrogen is by far the most common atom in the universe, and helium is number two. So we don't really even get to any metals until we get all the way down to magnesium. So the number one most common element is hydrogen, just like it's atomic number one on the periodic table. The number two most abundant element is helium, just like it's atomic number two on the periodic table. Then it doesn't follow that pattern anymore. Then it's oxygen is number three, neon is number four, nitrogen is number five, carbon is number six, well that is number six, silicon is number seven. So the first seven most abundant elements in the universe, none of them are metals. So because of abundance, when we look around us, we do not see a metal universe. We see mostly a non-metal universe. I've put here the abundance of the different elements, and I've made the size of the box that the element's name is in proportional to the abundance of the element. So obviously hydrogen is huge here. It is the most abundant element. And then helium is the second one, then oxygen. Now notice that all of those are shaded kind of greenish, like of a pale green color. That is the color that I use on my periodic table for nonmetals. The metals have a pale blue color. So notice way on over to the right, you see 12 Mg, that's magnesium. That's the first metal we encounter. And then as the abundance of elements snakes its way back through the universe into that nebula, you can see that there are more and more metals as you go along. But because the most abundant elements are all nonmetals, that means the things we see around us in the universe, including stars, including galaxies, including planets, and including living things like ourselves, are mostly made of non-metals. Now, by the way, this is what we call molar abundance, based on counting the number of atoms there are, not based on their mass. That's a little bit, it comes out a little differently if you base it on their mass. This is based on the number of atoms. Well, what if we were to look specifically at what's in our sun, not the whole universe, just what is in our sun? Well, it's very, very similar. You may notice that it's a very, very similar composition. But the noble gases are shifted a little bit later in the list, and a few things are moved up. But for the most part, it's still the same. Number 1, 2, 3, those are still the same. So our sun is made of hydrogen and helium. It's a glowing sphere of plasma made of hydrogen and helium. It's a little different when you get to the Earth, because the Earth is a solid object, so it needs some sort of solid structure to it if you think about it. And a lot of that structure is made up of what we call silicates. If you look at the background of this image, you see granite. So granite is a good example of a silicate. Silicates actually are made mostly of oxygen atoms, and then the rest of it is made mostly of silicon atoms, which of course is a metalloid. So if you're looking at the Earth, metalloids rate way higher when it comes to the Earth than they do in the whole universe or in the sun. And even metals rank higher in the Earth. Look at where aluminum is, and even sodium. They have moved up. And notice how the Earth basically doesn't have noble gases. Well, we do find helium, but there's a reason we have helium bubbling up through the ground, and that's because of radioactivity. We'll talk about that later if we have time. So even in the Earth, though, by a slimmer margin, the Earth is majority non-metal, just because of that oxygen. Okay. What about in the human body? When we look at the human body, or actually the composition of any living thing, it looks a lot more like the composition of the universe. In fact, if you went back to the one I showed you for the whole universe and plucked out the noble gases, it would look very similar to what we have in the human body, because we have no way of containing noble gases like helium in our body. The only difference would be you'd have to shift up carbon, because carbon makes up so much of our living tissue. Okay? So when you look at abundance in the human body, well, we are mostly nonmetals. If you look at the abundance of elements in the Earth, it's a little bit more nonmetals. In the sun, nonmetals. In the universe, nonmetals. On every scale, we live in a non-metal universe, and that is because of abundance. So those are the end of the notes on the periodic table. In the next notes, we will go into trends.